Yes.
Hey, what do you mean by a self-paced course?
Well, the course material is available in the form of video lectures. And there are multiple practice problems that come along as well. So, you can access all of it anywhere, anytime. And they are available to you for lifetime.
No way.
Oh, yes, way. Don't delay and enroll now.
Geeks learning together.
All right, so hi everyone, welcome back. A very good evening to you all, and myself Ayush Tripathi, and welcome you all to this post analysis discussion of the last weekly contest 201. So I will be taking this session off camera. So let me just quickly share my screen first, and I hope the screen is now visible to you all. So just write a quick plus one as a confirmation if it is visible to you. All right, so everything seems good to me. Starting with the first problem, which is named as beautiful matrix 1. And in this problem, you are given a matrix of a dimension n cross n, and your task is to determine whether the matrix is beautiful matrix or not. And here we have the definition for the beautiful matrix. And a matrix is considered beautiful if in every column there exists at least one beautiful cell, such that the value of that cell is equals to the sum of remaining elements in the same column. So let me explain you with this example. So let me just quickly draw it properly. So we have a matrix of a size 4 cross 4, the number of rows and the number of columns. So in a first row we have a 2, 0, 3 and 7. Then in a second row we have a 1, 4, 1, 3. Then we have a 3, 2, 1, 0. Then we have a 6, 2, 1 and 4. So we need to check whether the matrix is a beautiful matrix or not. And the criteria for the beautiful matrix, in each column we must have a beautiful cell. And a cell is called as a beautiful if its value is equals to the all the remaining elements of the same column. So in the first column, this last cell is a beautiful cell. Its value is equals to 6, and which is equals to the sum of all the elements of the same column. Then for the second column, this second cell is a beautiful cell. Its value equals to the all the remaining element of the same column. Then for the third column, this first element is having value equals to the sum of all the elements of the same column. Then coming to the last column, so the first element is a beautiful cell. This is a beautiful cell. So in each column we have a beautiful cell. So my answer in this case will be 1. So I will simply return true. I will simply return true. That is, yes, this matrix is a beautiful matrix. So it's a pretty easy problem. You just need to iterate over the matrix, and for every cell, just simply check what is the sum of this entire column. Just simply check what is the sum of this entire column, and whether this cell, whether the particular cell is having value equals to the sum of remaining element of the same column. And if it is, if we got any such cell, then we simply say this is a valid column, this is a beautiful column, and then we check for the next column. And if for any of the column, if we didn't get any beautiful cell, then we simply claim that the entire matrix is not a beautiful matrix, so we'll return false. Right? So this time we need to iterate over each column. So we simply run a for loop. So let's run a for loop. So here I'm going to write a pseudocode for this. So just simply run a for loop and iterate over all the column. So in my implementation, I numbered the column with the variable I. So I is equals to 0, and while it is less than m, that is up to m minus 1. And for every column, I will iterate over all the row. So j starts from 0 and it goes till n minus 1. So this is the way how we can iterate over all the column. And first you need to know the sum of this entire column. And let's say we are currently we are at this value. So first I need to know the sum of this entire column. So let's call this as a sum column. So it is equals to 0 plus 4 plus 2 plus 2, which is equals to 8. And from this 8, first I need to subtract this value 4. So the remaining sum of this column, it is equals to 8 and minus 4, which is equals to 4. And now this is the remaining value, and here I need to check whether it is equals to the current value or not. So the current value is mat of j comma I. So here j will give you the column number, and this I will give you the j will give you the row number, and this I will give you the column number. So isn't it a very pretty and simple solution? Now let me show you the implementation. So this is the method that you need to complete. So here I have taken the number of rows, then number of column, then I iterate over all the column, and for every column I iterate over all the row. So here I did one optimization. I will do everything with the help of this for loop. So here one observation that we can draw: if the maximum element of the column is not equals to the sum of remaining element of the same column, then it is not possible to have any beautiful cell, right? Because if there is only one possibility, that is maximum element of each column. If it is not equals to the sum of remaining element of the same column, then it is not possible to have any beautiful cell. So this is the observation that we can draw. So that's why here I have only taken the maximum element, and then I am just simply checking for this thing. So instead of writing in this way, you can also check if sum minus max. So sum minus max is the remaining element of sum, and if it is not equals to the maximum element, then we do not have any beautiful cell in this column, so simply return false. Otherwise, after getting a beautiful cell in each column, I will simply return true. So that's the complete solution of the first problem, and the time complexity is the size of this matrix, which is n cross n. Now coming to the next problem, beautiful matrix 2. So in this problem, given a matrix of size n, and a matrix is called beautiful if in each column there is at least one element that is equals to the sum of all the other element in that column, excluding itself, basically the remaining element of sum which is in the same column. And all these beautiful numbers, one from each column, must be in the same row. So this time we have a new condition. It is a follow-up version of the last problem. So this time we have a new condition, that is all the beautiful cell must be in the same row. And here some operation mentioned which we can perform. So in one operation we can increase or decrease the value of any element of this matrix by 1, and we need to return the minimum number of operation needed to transform the matrix into a beautiful matrix. So let me explain you with this problem, this example, this second example. So in a first row, so we have a matrix of size 3 cross 3, and in a first row we have a 2, then 4, and then again 4. Then in a second row we have 1, 2, 3, and in a third row again we have 1, 2, and 3. So we must have we must have a beautiful cell in each column, and all the beautiful cell from every column must be in the same row. For example, let's say I decided to consider this row 1. So that is, will make all of its cell beautiful. So how many operations do we require? So here in this case, it is already a beautiful cell, then it is also already a beautiful cell, then it is not a beautiful cell because the sum of remaining elements is 6 and the value of this element is 4. So I need to increment this value by 2. So here I need to perform the operation 2 times, and which is the minimum number of operation required to make all the elements of this row beautiful. So this will be my minimum answer. So my answer will be equals to 2. And if you check for all the other column, then you will require the operation greater than 2. So this is the minimum answer. But how I come to the solution? So the very first thing, I need to check this thing for every column, for every row. First I will check and try to make all the elements beautiful of this row. Then I will check and try to make all the elements of this row beautiful. Then I will check for all the elements of this row, and will find the number of operation required to make the element beautiful, all the elements of this row, right? And the very important observation in this problem, that is, we never perform the decrement operation. We never perform our decrement operation. So it is mentioned in the problem statement that in one operation you can increase the element and decrease the element. So in one operation you can increase the element or you can decrease the element. But my claim is that it is never optimal to perform this operation decrement. For example, and it is very basic reasoning. So here the value is 4. So here the value of element, it is equals to 4, and the remaining sum, it is equals to 3 plus 3. The remaining sum, it is equals to 6, right? So what are the possibilities I have? So one possibility which I have is to decrement the value. Just simply decrement the value of this cell by 1 and decrement the value of this cell by 1. So you might have some other configuration which is similar to incrementing the value of these two cells. So instead of decrementing the value of these two cells, what I will do, I will simply increment the value of this cell, right? So either you increase the value or you decrease the value. The difference will always reduce by 1. So yeah, that's the key idea. So the very first thing, I need to find the sum of each column. So this is the pre-computation that I will do. So let me write the steps here. So the very first step is to pre-compute the sum of each column. Pre-compute the sum of each column, and after the pre-computation, just simply iterate over all the cell. Just simply iterate over all the cell which are in the same row. So in this problem, the number of rows and the number of columns both are same. Basically, n cross n matrix will be given to you. So simply iterate over all the rows for I is equals to 0, and it goes till n minus 1. So this I is representing the row number. In the previous problem, it was representing a column number as per my implementation, but this time it is representing a row number. So this is I is equals to 0, then I is equals to 1, I is equals to 2, basically the third row. Then for every row, iterate over all the columns. So j is equals to 0 and up to n minus 1. Now the current cell, it is mat of ij, mat of ij. Cool. And here in this case, just simply declare a variable. Just simply declare a variable current, and this variable current will simply store the number of operations, minimum number of the operations that need to be performed to make all the elements of this row beautiful. So here I know the sum of a column, so it is already pre-computed, and let's call this as a sum. Let's say we have a sum array, and this sum array is of size n, and here sum of I will simply store the sum of all the elements of column I. So here in this case, how many operations do we need to perform to make the current cell beautiful? So here in this case, the remaining sum will be sum of j, that is sum of jth column, and minus the current element. So the current element is mat of ij. The current element is mat of ij, and here now I need to simply check how many operations do we need to perform. So it is simply equals to the difference. So the difference that we have, so which is, so I will increment the value of current by remaining minus mat of ij. Remaining minus mat of ij. These many operations I need to perform. And after this for loop, after iterating over all the column, and now we know the minimum number of operations required to make all the elements beautiful. So simply update the answer. So simply update your answer. So answer is equals to the minimum answer that we have so far. It might be possible when some previous column takes the lesser number of operation. So that's why some previous row take the lesser number of operation. So that's why the minimum answer that we have so far, and comma the current number of operation that we require, and we initialize this answer with some very large value. So let's say int max. So yeah, that's the complete idea, and the time complexity in this case would be the dimension of this matrix, which is n square. Now coming to the implementation. So this is the method for the second problem that you need to complete. So first I have taken the size of this matrix, then this is my pre-computation. Iterate over all the rows, and for every row iterate over all the column. So basically this is my this variable I is for the column, and this is for the row. So for the ith column, I will iterate over all the row, and this is my column sum, and simply I will store this value in a sum of I. So sum of I will simply store the sum of elements of ith column. Then initializing the answer with some very large value, then iterate over all the rows, then for every row all the column, and these many operations that we required to perform. So you can replace this value with the current. You can simply replace this value with the current, and here from the column sum, I am simply subtracting 2 into the value of a current cell. So basically, if you subtract it if you subtract the value one time, then it will give you the remaining sum, and again subtracting to find the difference, right? And finally updating the answer. So yeah, this was the complete solution for the second problem. Now coming to the third problem, which is a fairly interesting problem. So in this problem, you are given an array of integer ARR, and here you need to find the length of a longest subarray such that all the elements of the subarray are smaller than or equals to the length of the subarray. So here in this case, if we consider this entire array as a subarray, then it is valid. Here all the elements are less than or equals to the length of this subarray. So the length of this subarray is 3, and all the elements are less than or equals to 3. So now let's see how we can solve this problem. So the very first thing, let's analyze the constraint. Because if the constraint were very small, then I can iterate over all the possible subarray. And for every possible subarray, just simply find the maximum element of the subarray and simply check whether it is less than or equals to the length of the subarray or not. And if the maximum element of the subarray is less than or equals to the length of the subarray, then entire subarray is valid. And if entire subarray is valid, then simply update your answer. So this is one possible solution, and it is only possible when it is feasible to iterate over all the subarray. For example, here in this case, the value of n can be up to 10 power 5. The size of the subarray can be up to 10 power 5. So it is not possible to iterate over all the subarray. So let's say n is the size of array, and it can be up to 10 power 5. So if you iterate over all the possible subarray, then it will give you TLE, because the number of subarrays will be n into n plus 1 and divided by 2. So this is the order of n square, and this order of n square solution will definitely give you time limit exceed. Now, how we can solve this problem efficiently? So the idea here is to use the contribution technique, so which is again very interesting and very famous technique and super standard as well. So contribution technique. So contribution technique simply says that when it is not possible to iterate over all the possible subarray, then in that case we need to find the contribution of each and every element. So simply find the contribution of each and every element. So A1, A2, A3, A4, A5, A6, A7, A8. So here let's say the value of n is equals to 8. So here now I'm going to find the contribution of each and every element. So when I say contribution of each and every element, it simply means if I select this element, let's say this is the ith element. So if I select this ith element as the maximum element of the subarray, then what will be the maximum possible length we could have? So for example, let's say this a of 5, it is equals to 10. This a of 4, let's say it is equals to 9. Then let's say this a of 3, it is equals to maybe again 10. And let's say a of 2, it is equals to 5. And let's say a of 1, it is equals to 12. Then here let's say a of 6, it is equals to 9, or let's say it is equals to 8. Then let's say a of 7, it is equals to 15, and a of 8, it is equals to 2. So here currently I am interested to know the maximum possible length of the subarray which is valid, and the maximum element of the subarray is less than or equals to 10. So basically I'm going to select this element as the maximum element of the subarray. And now I need to maximize the length. So to maximize the length, I will simply find the previous greater element. So if I somehow know the index of a previous greater element, then I can easily find the value. I can easily check whether the subarray is valid or not. So here I need to know the index of a previous greater element, and also I need to know the index of a next greater element. So this is the previous greater element. So here let's say this is ps of I. So ps of I will simply store the, here I is equals to 5. So ps of I simply store this value. So ps of I will simply store 1, and it is index of a previous greater element, or I can say index of a previous greater element. This make more sense, or you can say largest index for which the value is greater than a of I. So here in this case, ps of I, it is equals to 1. It is equals to 1. Now, I need to know the next greater element, index of a next greater element. So the next greater element is a 15. So let's say it is stored in a array ng. So this is my array ps. Let's call the pg, previous greater, and let's call this array ng, that is next greater. So ng of 5 will simply store 7, that is index of a next greater element. And if you know these two values, then you can easily find the length. So what will be the length of this subarray? So it is equals to next greater element of I, minus ps of I, previous greater element. So pg, not ps. So it is a pg of I. Since next greater element and previous greater element both are excluded, so that's why minus 1. So here in this case 7 minus 1 and again minus 1, which is equals to 5. That is the subarray is of length 5, the maximum subarray length. So this is my subarray. For which the maximum element is less than or equals to 10. Less than or equals to 10. And now you need to check whether the subarray is valid or not. So now you need to check whether the subarray is valid or not. So how I can check this thing? So it is fairly easy and super straightforward. So you know the maximum length, and if the length of the subarray, if it is greater than or equals to this element, this maximum element of the subarray. So the maximum element of the subarray is a of I. So if it is, then the subarray is valid. And if the subarray is valid, then we simply update the answer. So how we update the answer? So answer is equals to the maximum answer that I have so far and comma the length of this subarray. Now the thing is how we can find the next greater element and the previous greater element. So this is a very straightforward application of a monotonic stack. So monotonic stack, this is a very standard problem and I'm not going to explain you this. So if you do not know what is monotonic stack and how we can find the next greater element and the previous greater element with the help of a monotonic stack, then you can just simply refer to some YouTube video or just go and read some article. But this is a very, very, very standard problem. So yes, this is a complete solution. And coming to the implementation. So this is the method that I need to complete. So taken the size of the subarray, then find the next greater element and the previous greater element. So by default, I am initializing the value with the -1. So assuming that current element do not have any element on its left which is greater than the current element. So there is an imaginary element which is at index -1 whose value is greater than all the element of the subarray. And the same goes for the next greater element. There is an imaginary element which is at index n out of bound whose value is greater than all the element of the array. Now this is my stack, and first here I'm going to find the previous greater element. So keep on removing the element if its value is less than or equals to the current element. So this time I'm going to store the indexes, and it is always helpful to store the indexes whenever it's come to monotonic stack problem. Most of the time it is helpful to store the indexes because from the indexes we can easily fetch the value, but from the values it is not possible to fetch the correct index. And this is a very trivial solution to find the previous greater element. Then I'm going to simply reset the stack, and this is for next greater element. So this is the logic to find the next greater element, and once I know the next greater element and the previous greater element, then this will be the length of maximum length of the subarray, and if it is greater than or equals to the current element, then it is valid. So simply update the answer, and finally I will return the answer. Now the time complexity for this is linear because this for loop will take linear time, and this for loop will also take a linear time. So the time complexity is order of n. Now coming to the last problem, which is an ad hoc problem, and for the last problem you need to know the simple observation. You need to draw a simple observation. So in this problem, you are given two integers L and R, and your task is to count the number of x in the range from L to R such that bitwise XOR of all the bits is 1. And since the answer can be very large, so return the answer under modulus 10 power 9 plus 7. So let's analyze the value of L and R. So the value of L and R can be up to 10 power 18. So it is not possible to iterate over all the element in the range from L to R. So we need to do something better. So let's analyze the first example. So here for the first example, the value of L it is equals to 1, and the value of R it is equals to 10. So let's write the binary representation of all the number in the range from L to R. and the binary representation of 10, 1 0, 1 0. So out of these 10 number, how many numbers are there whose bitwise XOR of a bits is equals to 1? So here in this case, the bitwise XOR of all the bits, it is equals to 1. Then then here in this case, the bitwise XOR of all the bits, it is also equals to 1. Then in this case, it is equals to 0. Basically 1 XOR 1, it is equals to 0. Then here in this case it is 1. Then in this case 1 XOR 1, 0. Then 1 XOR 1, 0. Then here it is also 1. Then in this case it is also 1, and it is 1 XOR 1, which is 0, and 1 XOR 1 again 0. Now in this case there are five numbers whose bitwise XOR of a bits, it is equals to 1. So my answer will be equals to 5. So my answer, it is equals to 5. Now how we can check this thing? So let's write a solve function. So I will write a function solve, and this solve function take one integer. Let's call this integer as a. So this integer a, and it will simply return you the possible value of x. So when I say possible value of x, so x is a valid number. It simply means it a bitwise XOR of all the bits is equals to 1. So valid numbers, count of valid numbers. When I say valid, it simply means the bitwise XOR of all its bit is equals to 1 in the range from 1 to 1 to a. So what will be my answer? So my final answer will be equals to solve of r, that is valid number in the range from 1 to r, and if I subtract the valid number in the range from 1 to L minus 1. So eventually I will get my answer, the valid number in the range from L to R. And this is a very standard step, because it is difficult to find the valid number in the range from L to R directly. That's why I will solve from 1 to R, and then I will subtract the result of 1 to L minus 1. So this is the first step. And the second observation, we need to check the number of bits, the bitwise XOR of a number of bits. Bitwise XOR of bits must be equals to 1. So if it is only 1, then the count of that bit is equals to 1. So this is another observation which is very famous and very standard. So bitwise XOR value equals to 1 if and only if number of set bits is odd. If the number of set bits are even, then the bitwise XOR will be definitely 0. So now my problem is, now the new problem is to count the number of integers in the range from 1 to a, in which the number of set bits is odd, right? So this is my new problem. So let me write it here. Solve of a. So solve of a will simply return you number of integers in the range from 1 to a, such that number of set bits in their binary representation is 1. not 1 but actually odd. So now let me give you an example. So here you need to draw an observation. Example, let's say the value of a, it is equals to 45. So the binary representation of a 45, it is 1 0 1 1, then 0 and 1. This is the binary representation of a 45. So 2 power 0, then 2 power 1, then 4, 8, 16, 32. So 32 plus 8, which is 40, then 40 plus 5, 45. So this is a binary representation of a 45. Now, the very important observation for this problem, let me write the binary representation of numbers from 0 to 7. So that is binary representation of the numbers from 0 to 7, which is less than 8. So the binary representation of 0, 3 times the 0 I can say, or let's say 4 times 0. Then binary representation of 1, then binary representation of 2, then binary representation of 3, 4, then 5, 6, and finally 7. Now if you notice one thing, then how many numbers are there for which the number of set bit is odd? How many numbers are there for which the number of set bits are odd? So here the number of set bits are odd. So I'm going to write O in case of odd number of set bit, and we'll simply write E in case of a even number of set bit. Now if you notice one thing, there will be exactly 4 numbers for which the number of set bits are odd, and there will be exactly 4 numbers for which the number of set bits are even. So if we have a count, which is which is the number of integers, then it is 2 power 3. It is 2 power 3. Then there will be exactly count by 2 numbers for which has odd number of set bit, and there will be half numbers for which there is a even number of set bits. So this is the main observation to solve this problem. You can also solve this problem without having this observation, but in that case you need to write some combinatorics logic, just simply NCR formula logic, and this is an homework task for you. But this problem can be solved very easily with the help of this observation. Now let's just quickly find all the numbers for which the number of set bits are odd. So now I'm going to fix the bit, and basically I will try to convert every set bit to 0. So here I will try to convert every set bit to 0. So starting with this set bit. So here starting with this set bit. So if I change this set bit to 0, then now I'm free to choose any configuration. I'm free to choose any configuration for these 5 bits. So how many possibilities I have? How many numbers are there? So there will be 2 power 5. 2 power 5 numbers are there, right? So there will be 2 2 power 5 numbers. So the value of count, it is equals to 2 power 5, which is equals to 32. And out of 32 integers, there will be 32 by 2, which is basically 16 integers are there for which the number of set bit will be odd. So I will simply increment my answer by half of this value. I will simply increment my answer by half of this value. So answer plus equals to count divided by 2. Just simply add this value in your answer. So answer plus equals to count by 2. This is the main formula, basically the complete solution. So how many values will be there? 16. Then coming to the next set bit, so this is 1, then this is 0, and now coming to the next set bit, and now I'm going to change this set bit from 1 from 1 to 0, and we'll check how many possibilities will be there. So if I decided to fix this bit to 0, then for all the three positions I'm free. I'm free to choose anything. I'm free to choose anything, right? But this time I need to know the number of set bits. Sorry, this time I need to know the number of integers for which the number of set bits are even, because here we have an additional set bit. So all the numbers which has even number of set bit, and if I add one bit to every number, then there will be odd number of set bit. And due to symmetry, we again increment my answer by the same factor, which is count by 2. So here in this case, the value of count, it is equals to 2 by 2 power 3, which is equals to 8. And out of 8 integers, there will be 4 integers. There will be 4 integers for which the number of set bits are even. And since here we have a one additional set bit, so this time we are interested to know the number of integers for which the set bits are even. Cool. Now coming to the next set bit, basically this one. So 1, 0, 1, and now I decided to change this bit to 0. I decided to change this bit to 0. So here in this case, now we are interested to know the number of integers in which the number of set bits are odd. So find the value of count. So the value of count, it is equals to 2 power 2, which is equals to 4. And out of 4 integers from 0 to 3, there are 2 integers which has odd number of set bits and 2 integers which has even number of set bits. So I will simply I'm interested to know the number of integers which has odd number of set bits. So it is equals to 2. So we'll increment my answer by 2. Now coming to the last set bit. So here in this case, 1, 0, 1, 1, then 0, and then this last set bit. If I decided to change this to 0, then in this case the value of count, it is equals to 2 power 0, as we do not have anything on its left. And now if you find the value of count, find the value of a count by 2. So count by 2, if the value of a count is equals to 2 power 0, then count by 2, it is equals to 0, right? 1 by 2, it is equals to 0. So this is an additional edge case that we need to handle. So if the LSP, the least significant bit, so if the least significant bit is 1, then I will increment my answer, right? If the least significant bit is 1, then I will increment my answer, because now I have two possibility. Now I have two possibility. Either we set this bit or we do not set this bit. So here in this case, there will be exactly one answer. There will be exactly one integer which contribute in your answer. So if you do not set this bit, that is, this bit is 0. So here this configuration is also valid, right? This configuration is also valid. It has odd number of set bit. And if you set this bit from 0 to 1, change this bit from 0 to 1, now this configuration is invalid. So basically out of these two possibilities, either 0 or 1, there will be one of these two possibilities is valid. So we'll increment my answer by 1. So if A and 1. Basically, this is LSP. If LSP is 1, then I will increment my answer. So this is one base case. And another base case, it might be possible when LSP is 0. So do I need to consider any other base case? Yes, there is exactly one base case. So for example, let's say A is equals to a very simple example. For example, let's say the binary representation of A, it is equals to 1 0 1 0 1 0 0. So let's consider this integer, and here the number of z bit, it is equals to odd, right? Here the LSP is 0, here the LSP is 0, but the number of z bit is equals to odd. So in that case also you need to increment your answer by 1. So if the LSP is 1, or the count of a set bit. So if the count of a set bit, if it is 1, if it is odd, if it is odd, if it is odd, then also we have to increment our answer. So in both the cases, we simply increment our answer by 1. So count bit and 1. So if it is odd, then also we simply increment our answer. And why is it true? Because you have considered all the possibility when you change this value to 0. You have considered all the possibility when you change this value to 0. You have considered all the possibility when you change the next set bit to 0. You have considered all the possibility when you change the next set bit to 0, but you forget to consider the possibility when we do not set and we do not change any bit. So that is initial value of this A. So when we do not change any bit, now I need to check whether it is valid or not, because all the numbers that we are testing here, all the numbers are less than A, but we also need to consider the number which is equals to A. So that's why this is the case that we have, and this is a complete solution. In my implementation, I will iterate from LSP to MSP, but here in my explanation, I have explained you from MSP to LSP, but both has the same meaning. Now coming to the implementation. So this is the method that I need to complete. So so my answer will be solve of R L minus 1, then plus this mod, and again take a mod. This is a modulus of subtraction. Whenever we subtract two number, this value might be negative, and then here I am adding this mod value to make it positive, and then again take a mod. Cool. And this is my solve function with the parameter A, and this parameter A has the same meaning which I have explained, and initializing the value of count with 0. So here one can skip this thing. So let me explain you over here. Yeah, this one. So here we are having a variable count, which is not required. So this variable will simply store the number of set bit, and this is the value of LSP, simply A and 1. Then initializing answer with 0. Then while the value of A is greater than 0, I am simply checking whether the bit is set or not. And if the bit is set, simply increment the value of a set bit. And actually we require the value of count, that is how many bits previously we have seen. So yes, we require the value of count, and here the number of integers that we have, it is 2 power count. If we have a three bits previously, then there will be 2 power 3 numbers, right? And I'm going to increment my answer by exactly half, and then simply discard this set bit. And this is my base case. If LSP is set or the number of set bit is odd, so in that case increment the answer by 1. And finally I'm going to return this answer. Here in this case the time complexity will be log of A base 2. So here I forgot to increment the value of count. So count plus plus. So this is same as we expected. So yeah, successfully submitted. And these are the complete solution for all the 4 problems of the last weekly contest. And thank you everyone for watching this video or joining the session. And see you in the next analysis. And have a good day. Good night.